All right, so now that we know the basics of stoichiometry, we can ask these bigger questions about if we have a certain amount of prod or reactant, like we did in the very first example, burning the steel wool of iron, and we know that that's going to produce iron oxide as a product. How much of this is being produced? That how much question, how much uh, we call the yield of the chemical reaction. So assuming this goes completely to this, and we know how many grams we started with, that's this concept of yield. And so I have a quick stoichiometry recap here with this sort of process flow. It can be helpful to just sort of break it down visually. So you start with the balanced reaction. Remember these coefficients here, these lowercase a, b, c, and d. These are the real keys. This is what relates the moles of A and B reacting together to the moles of C and D that are produced. And that's a really key relationship. So you got to start with this. And then if you are given the grams of A, then you can use the molar mass to convert from grams to moles, and that's because our balanced reaction is in moles, so we need to go from grams to moles, and that gives you moles of A. Now we use this balanced chemical equation to convert from moles of A to moles of B, and that's by just relating the coefficients, whether they're 1 to 1 or 2 to 1 or 2 to 3, whatever that may be, and then we convert back to the final grams of B, knowing the molar mass as our final conversion factor. And so if this feels foreign to you, jump back to video 3.2 and walk through that example. But we'll be doing this several times in this video when we think about the reaction yield, or how much of the product we can produce. So if we go back to this idea of yields, there are a couple different key concepts that we need to introduce. The first of which we've sort of already alluded to, which is the theoretical yield of a particular reaction. And so in the example where we're talking about iron burning in the presence of oxygen to make iron oxide, if we know that there are, say, 4 of these irons, 2 of these, and 3 of these oxygens, we know the molar ratios at which these things react. If we know also then that, say, we have 1.0 grams of iron to start with, we can use this stoichiometric process to determine theoretically if all 100 or if all 1 gram of this is converted at 100% efficiency to iron oxide, we could convert this and figure out stoichiometrically how much of this, what mass of this we would produce. So the theoretical yield is exactly that. It's the amount of the product, in this case Fe2O3, that's produced based on stoichiometry of this balanced chemical reaction, but assuming, and this is a really big assumption, that 100% is converted, meaning all of this 1 gram gets converted at a 4:2 ratio, molar ratio, to iron oxide. So that's a theoretical yield. As you can imagine, chemists would love to get theoretical yields of 100%, or actual yields of 100%. We would have much, much, much cheaper pharmaceutical drugs if this were the case. But there's a lot of factors that go into the fact that reactions actually don't go to 100% completion. That notion will be revisited a lot in Chem 108 when you talk about equilibria. But in this class, we won't really talk about the why as much as just noting that that's not really the case. In reality, we end up with yields that are less than ideal, less than 100%. We do the reaction to the best of our abilities, and maybe we get 46% or less in the actual amount of the product that we're producing. And so the percent yield then, so if actual yield is what you actually get when you do the reaction and you've got your flask with the reactant in it, maybe it's this iron oxide, you go and you weigh that final product, maybe you only get, 0.2 grams instead of the 100% yield that you thought. Then the percent yield is how much you got divided by how much you would be expected to get in the theoretical case. So if your theoretical yield, if you did this stoichiometrically and you figured out that, well, I should produce 2.0 grams theoretically if I get 100% conversion, you go through and you actually weigh it out using your actual lab skills. You weigh it out to 1 gram, then you multiply that by 100%. You figure out that really you only got 50% of what you theoretically could have got. So these yields are really an important step, and this forms the basis of virtually all of Chem 250. It's a major metric in chemical synthesis, which is what organic chemistry is. So you often do a chemical reaction, and then one assessment of how well you did the reaction is, well, what sort of percent yield did you get? What fraction of theoretical did you get? Did you get 98% or did you get 4%? Okay, let's run this as a quick example. So I've got a chemical reaction written up here, C2H4, which is ethylene gas. Just as an aside, ethylene is the stuff that you smell on fruit as it ripens. So it's sort of the rotten banana smell. That actually, if you mix that industrially with water at high temperatures and pressures, you produce this stuff, which is ethanol. So this is actually the industrial production of ethanol if you don't want to go through yeast fermentation. Okay, so this is a huge industrial process, and so this is a question that chemists or chemical engineers ask themselves when they work for these big companies. They say, well, what is the percent yield? So how much of this stuff do we actually get if you have 4.6 grams of the C2H4 to start with? So we got 4.6 grams of this, and we produced 4.7 grams of this. And we want to know the percent yield. And so remember, the percent yield is going to be equal to the actual divided by the theoretical yield times 100%. And we're actually already given the actual yield. This is what was truly produced. So we're going to know that the percent yield here is equal to 4.7 grams divided by whatever the theoretical is times 100. And so what we need to compute then is this theoretical yield, which will then allow us to compute the overall percent yield. How much did we actually get relative to what was theoretically possible? So again, we got to use stoichiometry, and we got to use a balanced chemical reaction. So the first step always is to balance your reaction. So pause the video and balance the reaction. So if you pause the video, you figured out that it's already balanced, or it should already be balanced, so we don't have to do anything there. So everything is then reacting in this nice 1 to 1 to 1 molar relationship that makes our work a little bit easier. Let's also then find the molecular weights of all of these compounds. So pause the video and find the molecular weight of each one of these individual compounds. Okay, so we've got the balanced chemical reaction as our first step. Second step, molecular weight. We just computed these by adding up all the atomic weights from their respective elements on the periodic table. So I've got arrows pointing to each one of these three. Double check my numbers, make sure that adds up. So the third step then is to compute the theoretical yield, and we're going to do that using our trusty tool, stoichiometry, which employs itself our tool of dimensional analysis. And so that is step 3 here. So let's start with what we know. And so we know that we have 4.6 grams of this stuff to start with. So 4.6 grams of C2H4. Let's set this up dimensionally like this. So we know the molecular weight, so we can go from grams to moles. And we want to know that because we already know the molar ratio. We know that 1 mole of this C2H4 reacts with 1 mole of the H2O. So we need to get to mole space. So we go to 28.05 grams of C2H4 for every 1 mole of C2H4. Let's get rid of our grams here just to be concise. So now we're in units of moles of C2H4. Now we can relate C2H4 to the moles of C2H6O that were being produced, because we're thinking about the theoretical yield. How much of this can we actually produce? And we know that they're produced in 1-to-1 ratio. So we can say dimensionally 1 mole for every 1 mole of C2H4, we are going to produce 1 mole of C2H6O, right? And so go back, let's get rid of our units. Now we're in units of moles of the C2H6O, our ethylene oxide gas. We're not quite done yet because we want to figure out the actual yield in units of grams, so that needs our last sort of piece of information, which is the molecular weight that converts grams to moles. So for every 1 mole of the C2H6O, we've got 46.07 grams of C2H6O. Right, and let's get rid of our sort of final unit there. Now we're left with grams of C2H6O. So you can pause the video or not. You can watch this. What you get if you compute this is 7.55 grams of C2H6O. And if we're keeping track of units here and sig figs, we're limited by the 2 sig figs here. So we'd probably call that 7.6 grams. Okay, so that 7.6 grams here, this is the theoretical yield of C2H6O that we would produce if we started with exactly 4.6 grams of C2H4 and we reacted them in a 1-to-1 ratio. And we assumed, again, this is at 100% conversion efficiency. So that's our theoretical yield. That's not our final answer, though, because we're being asked to compute the percent yield of the reaction. Okay, so the final step in computing the actual percent yield is to remember that percent yield is the actual yield that you get, which we were given. Remember, we were told that we produced 4.6 grams in reality, divided by the theoretical yield, which we just computed as 7.6 grams, so that's coming here, multiplied by 100%, and that's going to give us 62.2%, and sticking to the fact that we only have 2 sig figs in either of these numbers, we can only report this number with confidence to 2 sig figs. So that tells us that this reaction, the industrial production of ethanol in our instance, because we only obtained 4.6 grams in reality and we were supposed to obtain 7.6 grams if 100% was converted, that means we were only 62% efficient in our synthetic process.